Alright guys, welcome back to lecture 14 of machine organization. I'm going to divide this into two pieces today. First up, I'm going to be talking about binary arithmetic, and then to wrap up all of C programming, we're going to be looking at file input output. After this, we're going to be coming back to do assembly level programming. So that's going to be, I thought that just made a nice break, so we'll do this lecture in two pieces so that if you guys come back and review, there's a divider there. Okay, so let me jump right into this. Alright guys, so the first topic for today is addition and subtraction in binary, or arithmetic in general. So I just came back over here to a, this is just a text file opened up in Vim. I thought this might be the easiest way to do this because I can like walk through the process and point at specific things with my bold green cursor rather than just making a bunch of PowerPoint slides and using the mouse to circle what I'm talking about. I can actually do this live. I hope this is useful. Let me know if you prefer this to PowerPoint. We can put together the best possible presentation for next year. Okay, so I'm considering a 3-bit machine just to keep this simple as possible. This is going to be using 2's complement representation for negative integers. But the first thing that I want to do is talk about addition of unsigned numbers. So I'm looking at 3 plus 1, okay, in binary. So this is binary arithmetic. So 3 is going to be 0, 1, 1 on a 3-bit machine. So 1 plus 2 equals 3. And 1, whoops, that is the problem doing it live, is going to be 0, 0, 1. So when I go through and do my addition here, first thing I'm going to do is, I should fill this in with spaces so I can use the arrow keys. So the B0 position, 1 plus 1 is 2. Right, except the binary doesn't have a 2. So what I'm going to do instead is just like I would do with decimal addition, I'm going to put in a carry. So 2 is going to become 1, 0 in binary. So I'm going to stick a 0 there. And then up here in this row, in the B1 position, I'm going to carry a 1. And now I've got the same thing here. I've got 1 plus 0 is going to be a 2. So that's going to be represented as 1, 0. I'm going to come back up here. 2 is going to be 1, 0, so I'm going to carry a 1 into that position. And then when I come down here, place that with a 1. Oops. Let me make this look good. I'm failing with the typing. Okay, there we go. 1, 0, 0. So 1, 0, 0 is actually equivalent to 4 when we convert it back to decimal, which is exactly what we would get with the 3 plus 1. So the whole point of this problem was to demonstrate carrying, just like we'd see in decimal, but in binary. Alright, so my next example here, 5 plus 3, is going to be a demonstration of what happens. It's called overflow, when we create a number that's too big. So please remember, in 3 bits, when I'm using unsigned numbers, I'm allowed to represent 0 through 7. Those are the 7 is the largest number I'm going to be able to represent. Binary will be 1, 1, 1. So what happens when I get a number that's too big? So 5 plus 3 is 8. Let me just write this over here. 5. There we go. 5 plus 3. And in binary, 5 is going to be 4 plus, no, 2 is plus 1. And 3 is going to be, just like I had up above, 0, 1, 1. So when I do this addition, there we go. I know the answer is going to be 8. Let's see here. So let me just walk through this. 1 plus 1 is 2, which is going to be 0, carry the 1. And then 1 plus here 1 is going to also be 2, so I get a 0, carry the 1. Come on, Mike, you can type. All right, 1 plus 1 again is going to be 0, carry the 1. And then I'm just going to carry this down. The problem is that I only get 3 bits to represent this. And so what happens is that I keep the smallest 3, the 3 least significant bits. So when I store this in memory, this is going to become just 0, 0, 0, which is going to be 0 instead of 8. So here, check this out. I just real quick filled in all the possible numbers for unsigned integers with 3 bits. And what I'm seeing here is I started with 5. I added 3 to it, so 1, 2, 3. But what happens is it wraps around. So if I were to do any of these, it's sort of like taking the modulus of the answer based on how many digits I get. And because I have overflowed how many bits I get at the end to represent my final answer. This sort of, I want to call it a mistake, but this is just how it's going to work. It is known as overflow. This is actually pretty common to see on machines. If you're doing like, if I'm using an integer or a small to represent a number that's just straight up not big enough to hold the result of my computation, like if I'm looking at the Fibonacci sequence or a factorial type problem where the results get very big after just a few iterations of those algorithms, this overflow problem is quite big. All right, and a great way to test to see if overflow has occurred is to just take a look at your two numbers. So in this case, I've got 5 and 3, and your answer. If I add any two numbers together and the answer is smaller than the larger of those two numbers, then overflow has occurred, and I no longer have the correct answer because I've lost some of the more significant bits. All right, so quick way to test for overflow. All right, so subtraction is going to work the same way whether we're using signed or unsigned numbers. So, but I wanted to just real quick do an example with something I would work with either. So signed subtraction. So in this case, I'm looking at 2 take away 1, and 2 in binary with 3 bits is going to be 0, 1, 0, and take away 1 is going to be 0, 0, 1. So the first thing I'm going to do is, just like in decimal, I'm going to go ahead and say, okay, 0, take away 1. I can't do that. So what I'm going to do is I'm going to borrow from the next decimal place over. So in this case, this is going to become a 0. Here, let me actually leave the number there and just right up at the top. This is going to become a 0. Oops, right there, a 0, and this will become a 2. Now I can think about it like that while I'm doing the math. So now I can say 2 take away 1 is just going to be 1. And then I'm going to make 0 take away 0 is going to be 0, and 0 take away 0 is going to be 0. Make the numbers all line up. So hopefully that makes sense. I'm borrowing from the 2's position here and turning this 0 into a 2 for the subtraction so that I've got something to actually subtract from, because I need to be able to take from a larger digit in order to get a meaningful answer right here. So hopefully this subtraction worked. This would be an example that would work for either signed or unsigned numbers here. So the next example I want to do, I want to look at signed addition a little bit differently. This is technically a subtraction problem. But what I've done here is taken my subtract 1 and turned it into an addition of -1. So here, check this out. This is going to be how this works. So let's see here. I've got 2, again, -1. We'll just write it like that. So this is going to be 2, it's still going to be 0, 1, 0. I need to fix my Vim RC so it stops auto-filling that in and not letting me just keep typing. I haven't done that yet on my own machine. Okay, so take away -1. Let me just make a note real quick here. That -1, I'm going to do this in a couple of steps. If it were positive, it would be 0, 0, 1. In 2's complement, to switch from positive to a negative, I'm going to first take the 1's complement. So 0, 0, whoops, the 0 turns into 1, the 0 turns into a 1, and the 1 turns into a 0. So that's how 1's complement works. Make a note right here. 1's complement, and then I'm going to add 1. So plus 1 is going to be 0, 0, 1. And then the result of that. So I'm looking at the second line here. 0 plus 1 is going to be 1. 1 plus 0 is going to be 1. And 1 plus 0 is 1. All right, so -1 in 2's complement representation, 1, 1, 1. Here, one sec. Let me write out all of these, and I'll just have the whole chart available for reference. All right, so just for quick reference, the very first bit here is going to represent the sign, but it's a little more complicated than that. But anyway, if it's 0, we're just going to get the normal positive numbers that we'd see for signed magnitude, for unsigned magnitude. Okay, but if this bit is a 1, the formula we use would be to take the negative of the 2 to whatever power this is. In this case, 0, 1, 2. So -2 squared, because it's the B2 position, so I'm raised to the 2 power. So it's going to be -4, take away -4 plus 0 times 2 to the first times 0 times 2 to the 0th power. So that just gives me minus 4. And this is going to result in a pattern where the very bottom number, the 1, 1, 1, all ones position is going to be minus 1, and then it just counts down from there, minus 2, minus 3, minus 4. Okay, so easy way to remember this if we're looking at small numbers at least. For larger numbers, go ahead, just grab that formula to do the conversion if you need to. Go from binary to decimal. All right, otherwise, 2's complement representation means just we take the 1's complement and then add 1 to it. Those are the 2 steps we need. All right, so now back to signed addition here. So I'm taking 2 plus negative 1. So I've got 2 here is 0, 1, 0. Negative 1 in 2's complement is 1, 1, 1. So now I'm just going to finish this problem up. When I add these numbers together, 0 plus 1 is going to be 1. And then 1 plus 1 is going to be 2. So I need to do that carry thing. So I'm going to get a 0 here and a 1 here. 1 plus 1 is 2. So I'm going to also see the carrying issue. 0 and then 1 right there. And when I take 1 plus 0 plus 0, essentially, I'm going to get a 1 right there. And now I only get 3 bits. So this is actually going to be stored as 0, 0, 1. So we see that this same problem, 2 plus negative 1, also is going to give us the exact same answer, 0, 0, 1, just like we'd expect. 2 take away 1 is 1. But it did this by overflowing the fourth position there. So that's not available for us to store a number in. So subtraction with signed integers still works just the same, whether I'm like just doing regular subtraction or I convert to a negative number and then add them together. They work the same. All right, one more slightly more complicated example is going to be a problem where I am subtracting and end up with a negative number. So let's take a look at how this is going to work. All right, so I'm going to take 2, take away, insert mode, take away 3. So in binary, 2 is going to be, let's see, 0, 1, 0, and minus 3. I'm just going to look at my chart right here since I already did all the work. It's going to be, let's do it with regular 3, 0, 1, 1. And we'll just do some subtraction here. So as I go through this, I'm going to need a line for carrying and borrowing, or let's see, whatever it's called. So I'm taking 0, take away 1. What I'm going to get here is I need I'm borrowing. So my 1, 0 is going to turn into a 0 and a 2. Okay, and when I do that, 2 take away 1 is going to be 1. No problem. All right, now I run into a problem here because I've technically got 0 take away 1 again. And I would just normally borrow from this position right here, but there isn't anything. So instead what I'm going to do is jump over here to this imaginary fourth position. There's nothing there. Technically it'd be 0s all the way out for 2, but instead what I'm going to do is I'm going to borrow from this imaginary missing bit right here and just pretend that it works. So this is going to become a 2 right here, and I'm going to borrow from that position. So maybe one more line up here. This represents my first level of borrowing. And then up here, what I'm going to end up with is a 1 and a 2. Let me think, did I do that right? Because I'm borrowing from this position, so that becomes a 2. And then I'm borrowing from that position, so that becomes a 1, and this becomes a 2. All right, and then, yep, 2 take away that 1 right there from the minus 3 line is going to be a 1. And then 1 take away 0 is going to be a 1. And, oops, messing up here. 1, 1, 1 in binary is minus 1 for negative 2's complement representation, which is exactly what we'd expect if we take 2, take away 3. So the trick here was that I needed to borrow from this imaginary, I'm hesitant to do this, but if I stick in a, could be 0, could be 1, I'm borrowing from this piece right here that's not actually there. I'm going to take out my question mark in just a second to leave it so that when I post this on Canvas, it looks normal. So it's not confusing for people who are looking at this document first. So there, take that out. Okay, but anyway, so the trick here was that I had to borrow from this imaginary fourth bit position that doesn't exist. All right, one more example, and then I'm going to wrap up addition. All right, so the next problem I'm going to be looking at is -2 take away 3. The answer here is going to be -5, but here's the problem and the challenge. The reason I chose this particular problem is we don't actually have a -5 that we can represent. So just what happens here, this is a problem known as underflow, and here's the idea. Okay, so I've got -2, I'm going to be subtracting 3 from it. So if I go over here, -2, I'm just going to grab this from my chart. It's 1, 1, 0, 1, 1, 0, and then I'm going to be subtracting 3. So I'm going to go ahead with the +3, 0, 1, 1. We'll do some subtraction. Come on, insert mode. Nope. Insert mode. Okay, 1, 1. Whoops, 0, 1, 1. Okay, so doing some subtraction here. So what I've got is I'm going to be borrowing for this first piece, because 0 take away 1, I can't do that, I need to borrow. So I need to turn this into insert mode. Come on, Mike. 0, I'm going to borrow from that. That'll be a 2. Man, I got to fix the vimRC, make this easier to type. Okay, 2 take away 1 is going to be 1. There we go. All right, and then same problem here. I've got 0 take away 1 is going to be, yep, I need to borrow again. So let me add another line here. And I'm going to borrow from this position, so that'll become a 0. This will become a 2. And now I'm going to take 2 take away 1 here. That's equal to 1. And now I've got 0 take away 0, so that's going to be 0. And now in the end, I do not get, here, 0, 1, 1. The first bit 0 tells me it's going to be a positive number. And in fact, it's going to be +3. I can either look at my chart up here, or I can just say 1 plus 2 is 3. And -2 take away 3 is -5. It is not 3. But here's what happened. I've underflowed this, so there is no -5. So basically, I started with -2 right here. I'm subtracting 3, so that's basically like counting up 3 positions, 1, 2, 3. I ended with a positive number, even though my answer should be negative. I just don't have enough bits to represent that negative number. So -5, I would require 4 bits. All right, so that's going to wrap up arithmetic. If you guys have any questions, post them on Piazza. If you want to see another example or something, you can propose that, and I'll go ahead and do it in the solution box. All right, next topic, file, input, output. Be right back. All right, guys, so the next thing I want to talk about is reading and writing to files. So looking at what we've got right here, this is my file1.c. I've got 3 examples for us today. This is just an example of opening a file and reading from it. So if we go through here, I'm defining max. This is a great way to just create a constant that I'll be using for the size of everything, because C does not dynamically allocate things. For example, right here, I'm creating a character array to hold all of the data that's being read from the file in buff. And let's see here. I'm also creating a file pointer variable. So check this out. The star here tells me it's a pointer. This is a file pointer. So this is just going to be a stream of characters that we can read in from. To use that, I'm going to assign that file pointer from the function fopen. And the file I'm reading, so here are the options. The file I'm reading is going to be this gatesquote.txt file. That should be available in the code download section on Canvas. And we're going to be opening this in read mode. One sec, I'll pull up the man page for fopen. We can see all of the different options. Okay, and then what we'll do with it is we're going to just go through. We're going to use fgets. This is going to just read a string of bytes from the whatever the file pointer is pointing to. And it's going to read at most this number of bytes. So this is why I'm putting this in here. If I didn't have this maximum value to decide how big my character array is, I could easily overrun this buffer and fill it with more characters than will actually fit in memory. So this is why I'm using this numerical constant for the size of things. Way better than hard coding, because I only have to change it in one spot if I'm suddenly going to be reading a bigger file. I'm doing this in a while loop right here. fgets is going to read until it runs into an end line or an end of file marker, and it returns that either the character it reads, or if it reaches the end of the file, it returns the ELF which is going to evaluate to false in a while loop. Again, I'll pull up that man page in just a second and highlight these. Then all I'm going to do is print out that buffer as a string. And then at the very end, I need to close my file pointer with fclose. This is important because you can only have so many files open at a time. When this program ends, the operating system will take care of closing all those files for me if I forget. In my third example, I'm going to talk about something that doesn't do that. It's just very good practice to make sure that even if we only have one file open, that we remember to close it when we're done. And this is is talking to the operating system, because there's a communication there between the disk and your program in C. All right, let me go run this. We'll show you that it works. You can read the awesome quote, and then I'll pull up those man pages. All right, guys, so I just compiled it successfully, and I'm going to run it in 3, 2, 2.5, 1. Okay, so there you go. The computer was born to solve problems that did not exist before by Bill Gates, one of my favorites. And we can see that it's working. If I go to that file, let's see what I call it. Gates. Yep. I can just see there's the only thing in this file is that quote. You guys can download that yourself. Let's get out of here. And now I was going to pull up the man page for fopen and take a look at that. I wanted to highlight a couple of things. Let's see here. Yep. So it requires a path name. In this case, I can either give it a character pointer, so a pointer to basically a string in C, or I could, what I did was I just hard-coded the file name as a, inside quotes, as a string literal. And then it also requires that a character for the mode. This is, again, going to be a character buffer, so if I'm putting this in a character pointer, so if I can have more than one character here. Let's see here. I wanted to highlight, let me scroll down a little bit, all the different modes that are available to us. So I was using R, so this is just going to open the file for reading. If the file doesn't exist, it's going to return null. So I'm going to go back in a second and add a check for that, because I didn't do that. That first program doesn't have great programming style practice. R+ will open it for both reading and writing. It's the same thing more or less as W+. I believe this one will fail if the file is not open. It'll return null, and this one will create a new file if it does not exist. So that's the difference between the W and the R+ version. And if we just open a file with W, even if there's a file there, it's going to delete the contents of the file and prepare it for writing. So we're going to nuke whatever's in the file. A is sort of the append version of that. It's going to keep whatever's at the file and put the position where it's going to write at the end of the file. And A+ is just going to create the file if it doesn't exist. If I'm reading, or if it allows me to read from it and append to the end. So if I just go ahead and start writing text to this, it'll just put it at the end. Okay. We can also add the character B if I'm writing to write the text in binary. So WB would write in binary. There we go, right there. And where's the return stuff? Yep, the return value upon successful completion returns a file pointer, which is a non-null pointer to like a location in memory. It's treated just like reading from memory. Otherwise, null is returned. Error number is set, so you can read that from the command line later. Okay, yep, so that's what I want to do here. And then I also wanted to open the man page for fgets. All right, there's a bunch of different versions of getting data. This is just another way to read from an input stream, like the keyboard or from a file. So the version I'm using right now is this fgets. I gave it a character buffer to fill in. I told it how many bytes I want to read, and then I gave it a source, and this was my file pointer. So basically fgets with a C is going to get a character. Fgets without that is just going to read however many characters I tell it to. And the return value, this is the part I wanted to focus on, is the character that's read cast to an integer or EOF. And EOF is going to evaluate to false if I use that as a condition. All right, let me move on to the next example. I lied. I wasn't quite ready to move on to the next example. I wanted to show that I did not do great programming practice here. I'm using fopen without ever testing to see if this file really existed. So here's what I'm going to do instead. I'm going to just add a conditional. If fp is equal to null, that means this has failed. So instead what I want to do is just return 1. And the 1 there would be a signal that this is an error. It did not return normally. Could also use exit 1. That's a system call that's going to just crash the program immediately. I would prefer that one if I were using this inside of a function, because that will end no matter where I am. Return inside a function will just parentheses where I don't need them. We'll just go exit the function. Okay. Let me make sure this still works. I didn't mess up. There it is. So no problem. Next example. Alright guys, so in this example I'm going to be writing to a file and then reading it back just to make sure that it really worked. And again, all of this input-output stuff is just in standard I/O. So, and again, to use this, I'm going to open a file. So I'm creating a file pointer. So this is going to be a location in memory where I'm going to be interacting with my file through the operating system. Fopen returns that location as a pointer. And I'm using WB as my option here. So I'm going to be writing this as a binary file as opposed to an ASCII file. You guys can experiment by taking that B off and just see the difference. All right, and I'm calling the file bar.bin. So foo and bar are typically used when we don't know what to do for a file name. So I'm going with bar this time. And bin is sort of the abbreviation for a binary file. If I were writing this as an ASCII text file, I would have gone with txt. And here's what I'm doing. I'm just going to write down this number, hexadecimal, 1 through 8. All right, now, because I'm opening in write mode, I'm going to use fwrite as the C command to write to a function. That takes 4 options in this case. I need to tell it what I'm writing. And this is going to be more or less a pointer or assigned to a pointer inside. So I need the address of something if it's just a variable. If it's already a pointer, I can just leave this as without the address of. And this is going to write a number of bytes, but it's going to do it in, it takes 2 options to get there. So it's going to ask for the size of whatever we're writing. So if it's an integer, if it's an object, if it's a character, I'm just going to give it however many bytes are in my integer or character or short or whatever, system dependent, may change in the future. And then how many of those things I'm writing. So it's assuming that I'm giving it an array. And if I have a string, I want to make sure this is big enough to include the entire string. And then where to write. And again, this is this file pointer is how I'm interacting with the operating system to make sure this gets put on the disk. And as always, close your files. We only get a certain number of them open. And again, this version where I'm using fopen is going to return the file as soon as the program is going to close the file for me. When I get to the end of my program at this return line, operating system will take care of that for me. But it's good practice. Okay, now in part 2 of this, what I'm going to do is I'm just going to go ahead and open my file again. I'm going to reuse that same file pointer. So this will just be assigned a new memory location where I'm interacting with the operating system to open that file. And I'm going to be opening it in read and again binary mode because this is a binary file. Declare a variable so I can read the number into it. I don't want to use this same one because that already has the number, and I want to show you guys for real that I'm doing this correctly. So we'll be reading that number, and again, fread takes a location in memory where I'm going to be storing something. This is not a pointer, it's just a regular variable, so I need the address of that. And again, fread requires what I'm writing, the size of whatever I'm writing, how many bytes. There's another option here for if I'm giving the size of number of bytes and how many integers I'm reading or how many things I'm reading. And then the pointer where this goes to. So this is the 4 option version of that. All right, and then, yep, I'm just going to print this out to the screen as a hex number so I can see that it worked. And again, I'm closing my file pointer. All right, let me go ahead and run this. And here, I'll cut the video so that you guys just see the results and don't need to watch me type. All right, guys, so I compiled it. There were no errors. I'm running it. And what I can see is that the number that I read in is indeed 1, 2, 3, 4, 5, 6, 7, 8. So it looks like it's working. All right, and just one more thing before I move on. If I list the contents of my directory, I can see I've got bar.bin right here. And if you remember from like lecture 3 or something, we have this hex dump command. I may have used octal dump back then, but anyway, hex dump -x, there we go, -x, and then bar bin. I can read the contents of this file. So this first number here is the position number. This is the memory location, essentially where the file begins in bytes. And then it's I've got the number here, 1, 2, 3, 4, 5, 6, 7, 8. But we can see is that they chose to write the bytes in what I would consider an interesting order. So at position 0, we've got 56, and then at byte 1, we've got 78, and then at position 3, we've got 12, and then 34 wrapping it up. And then nothing, this would be the end of the file here at byte 4. So there we go, that's what it looks like. All right, guys, I just want to show you one more way of writing to files. I'm using open here instead of fopen, and I'm using write instead of fwrite, and close instead of fclose. These three are actually Linux system calls, and C will let us do that. So this is not regular C programming. It's calling a Linux program. So I don't believe this works on Windows or on a Mac. It might, and it may behave differently. One of the major differences is that if I'm using a system call to open a file, it's not automatically closed when this C program ends because it's not a C function. And the operating system will leave it open for us. So this one's a little more dangerous in my opinion. You have to remember to close your file. So the way this open works, it just requires the name of the text file, or the name of the file we'll be writing to. And then it has all of these different options. We're using the OR here. So this is actually creating a bit field. So all of these would correspond to one bit in an integer that gets passed in. So O stands for option. I'm going to be creating a new file. I'm going to be writing only, so I won't be reading. And I'm going to be writing at the end of whatever's already there. This create doesn't like nuke whatever's there. If it just creates it if it doesn't exist. I don't remember what this one does. I copied this code from someone else. All right, and then this FD, the value that it returns, is sort of the operating system control number for that file. You can print it out and see what it is. It's assigned a negative integer if this open fails, so that's what we're going to test for to see if there's an error. And you guys can go open the man page and read exactly the return type of this, just to refresh your memory if you're ever using it. But here's the idea. Oh, I also wanted to highlight that I'm using fprintf a little differently. So we've been using printf up through now. That's printing a format string. The F here in the front says we're going to be printing to a file, just like fopen, fclose, fwrite. Fprint is printing to a file, and it takes as an argument whatever file I want to print to. By default, the printf without the F is going to go to standard out, stdout. That is the screen. Standard error by default also goes to the screen. This F just means I get to tell it where I want to write, and I can use the name of a file right here, or a pointer to a file. Pointer to a file to decide where this goes. So in this case, I'm just going to be writing to the screen. A lot of times you'll redirect this standard error to like a log file or something, or an error file, so that if your program crashes, for example, in the future when you guys are working on real production code at your job, you'll probably have something like this that should your customers find out that the program crashes, you'll want them to send you an error log so you can fix the bug, rather than just trying to guess what they were doing. This is how you'll do that. All right, and then we're, let's see, down here we're using write instead of fwrite. And again, this is a Linux system call. It takes that, which file I'm writing to, and they're given like an ID number. And then the next argument is what I'm printing, in this case, hello world. And this is how many bytes I'm going to be printing. And this needs to be at least equal to however many bytes right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've got one extra for the end of file. And then close this. Definitely close it. All right, let's go make sure this works. All right, so let me see here. I'll go ahead and do the, grab that. This is file 3 and 3. All right, then we'll just run this. File 3. Now I should see that I have created testfile.txt. And it wrote it out as a binary file, so this program actually believes that this is executable. Let's take a look at it. and just verify that it is written in ASCII code. So we can actually see Vim will translate anything that's in ASCII to this characters we can read. And then this stuff at the end is garbage because I printed one extra character that cannot be printed as an ASCII character. All right, I'm actually gonna wrap up this video, go get this produced, because this ends the C programming part of the course. And then part 2 of the lecture will be diving into the beginnings of assembly programming. So let me go do some editing. I'll put this video up on YouTube and then start working on the second half.